All right, let's dive right in. Today, we're talking about self-driving cars, but not the parts you usually think about, like the cameras or the steering. Nope, we're going under the hood to look at something invisible, but maybe the most critical piece of the whole puzzle, how these cars actually talk to each other.
I mean, just look at a scene like this. It's chaotic. Now imagine every single one of those cars is driving itself. How on earth do they coordinate? How do they share life or death information in the blink of an eye to avoid a collision? That right there, that's one of the biggest challenges facing the future of driving. So the magic that makes all this possible is a technology called Vehicle to Everything, or just V2X. It's exactly what it sounds like. It's a massive wireless network where cars are constantly talking, not just to other cars, but to traffic lights, to roadside sensors, everything. The entire city basically becomes one giant connected moving brain. But here's the massive catch. This network is never, ever still. It's constantly changing shape. We call that its topology, every single fraction of a second, as cars weave in and out of traffic. Trying to manage this high-speed dance, is a huge problem. Because for safety, every single millisecond counts. And the bottom line is, our old ways of managing networks just can't cut it. They're way too slow. They try to solve these problems that are, in computer science terms, NP hard. All that really means is that as you add more cars, the time it takes to find the perfect solution just explodes. You don't have that kind of time. What we need is something new, something that can see the network's shape, its topology, in real time and make smart decisions instantly. We need an AI.
And that brings us to the hero of our story, a very special kind of artificial intelligence that's built specifically for this job. It's called a graph neural network, or GNN for short. So what is a GNN? Well, think of it this way. It's an AI that's designed to think in terms of connections and relationships. It doesn't just see a long list of cars and their speeds. No, it sees the whole web. It understands the structure of how everything is connected to everything else. So how does it actually learn? It uses a really cool process called message passing. Honestly, the best analogy is a social network. Each car, or node, sends out little messages to its neighbors, the other cars it can connect to. These messages have info like, hey, I'm here, I'm going this fast, and our connection is strong. The GNN then gathers all these messages, layer by layer, so every car gets a really rich picture of what's happening around it. Okay, so we have this powerful AI. But how do you actually get it to understand something as messy and constantly changing as a real traffic situation? How does it truly learn the network's shape? Well, it all starts by translating the real world into a language the AI can speak, and that language is a graph. So every car and every roadside cell tower becomes a node on this graph, and the communication links between them, those are the edges. Simple as that. Right, so that works for one snapshot in time. But what about a second later, when all the cars have moved? How does the AI actually perceive these constant, high-speed changes happening out on the road? This is how. This chart is basically the GNN's vision of the network. It creates a digital fingerprint, called a graph embedding, that represents the entire network structure at any given moment. When that line is kind of flat, the network is stable. But every single one of those giant spikes, that's the GNN detecting a huge change in the network's shape, like a bunch of cars suddenly entering an intersection. It sees it happen instantly. Now, being able to see the network like this isn't just some neat party trick. It's what allows this AI to solve some of the most critical, high-stakes problems in vehicle communication with mind-blowing speed and accuracy. Let's talk about handovers. That's when your car needs to switch its connection from one cell tower to the next. You don't want that to fail. The GNN can predict when a handover is needed with over 93% accuracy, making sure that connection stays rock solid. And speed? What if a car's main signal is blocked and it needs another car to relay its message? The GNN can find the absolute best car to do that in less than 5 milliseconds. That's faster than you can blink. It's almost instantaneous. So you might be thinking, okay, it's fast, but are we sacrificing accuracy? And the answer is a resounding no. When you compare the GNN to the old, super slow methods that crunch numbers for minutes to find the perfect answer, the GNN gets a result that's nearly 96% as good. But it does it thousands of times faster. You get the best of both worlds. So what does all this mean in the real world? It means safer, more reliable self-driving cars. It means connections don't drop during a critical moment. It means the whole system is just tougher, smarter, and way more robust.
And, this technology is so much bigger than just cars. This is a fundamental building block for the entire future of wireless communication.
GNNs are tailor-made for the incredible complexity of future 5G and eventually 6G networks. They're the key to managing resources on the fly, and they fit perfectly into new, flexible network designs like O-RAN. What we're really talking about here is paving the way for networks that can manage themselves, heal themselves, and adapt to pretty much anything.
So we've seen how this topology intelligence can bring order to the chaos of a city full of autonomous cars. It leaves you with a pretty big question, right? If an AI can manage a network that complex, that dynamic, and that critical, what's next? What other massive, real-time systems could it learn to orchestrate?